Yeah, so I think we can start. I'm Bhargav. I'm a PhD student in IISc, and every week from 4 to 5 on Saturdays, I'll be taking problem solving sessions for this course. So let me present my screen. Yeah, so if anyone of you has any questions, just like unmute yourself and ask. Because that would be better than writing it in the chat because I can't always see the chat while I'm presenting my screen. Okay, yeah. So is my screen visible?
Yes.
Yeah. Okay. Second, someone wants to. Yeah, someone wanted to join the meet. Yeah. So first, we'll just quickly recall what we have seen in this week. So the first thing that we would have seen is the time hierarchy theorem, or the deterministic time hierarchy theorem. So, can someone tell me what this theorem is? Okay, so yeah.
So if we give more time to the Turing machine,
Mm.
then it can recognize the language. If this, I mean, so if we give, I mean, more time to the Turing machine, then definitely we can decide more number of the languages. But then this time difference should be greater than the log of something, log of n, I think.
Right. Yeah. So the formal statement is this: the class dtime of fn, that is all languages that can be decided by a deterministic Turing machine in fn time for some function n, is strictly contained in the class dtime gn for any gn such that fn log n is equal to small o of gn. So for example, what this says is the following. It says that dtime n is strictly contained in d time n square. So, so what this means is that there exists a language which a deterministic Turing machine can decide in time order n square, but not in time order n. So, if we give more time to the Turing machine, it can decide a larger class of languages. Okay. Yeah, so the next thing you would have seen is some space complexity classes. So far we have been seeing classes like d time, nd time, or n time, p, np, etc. In all of these complexity classes, the computational resource that we are worried about was time. But there are situations in which you are more worried about how much space you are using. For example, consider a situation in which you have a sensor, let's say in a mine, and its job is to determine whether a fire has started or not, depending on whether like the temperature has suddenly gone up, or like there is a lot of smoke in the mine or something like that. Now for such sensors, these sensors would sort of they would be powered by batteries, right? And if you have if that sensor like takes up a lot of has a lot of memory, it would also end up using a lot more battery, and you would have to replace battery like very frequently. So there, in such a situation, you would want to be able to do as much computation as possible in as less space as possible. So space is also like a valid computational resource that we can worry about. So just like there are time complexity classes, there are also space complexity classes, and the first class that you would have seen would be the class dspace fn, and this is just the class of all languages that can be decided by order fn space deterministic Turing machines, that is deterministic Turing machines that require order fn space. And you would have seen the class p space, which is the class of all uh, languages which can be decided in polynomial space. So it's a union over k greater than equals to 1 of d space nk. So is everyone okay with the definition of d space and p space?
Yes, but then I'm not that much okay with the definition of the time hierarchy theorem.
Right.
Definition is fine, but then why this log component appear here?
Okay, so uh, I don't know whether you know this or not, but there is this theorem that says that basically if you, so do you know of a universal Turing machine?
Yes, so this fact was told by sir in the class that
Right.
if a machine is simulating the other machine,
Yes.
then it requires the log n amount of the, I mean log n extra time to
Right.
say a machine which runs at the time say fn. So the machine which is simulating it would require the time of the order of fn log n.
Right.
But my query here is that from where did we get this log n term? We are probably is it because that to differentiate that gn indeed is greater than fn, Turing machine itself would be taking some time. That yes, indeed this gn is greater than fn, and this amount has to be greater than log n. Uh, I mean, or is there any other reason
So, I,
behind this log n stuff?
so as far as I know, the only reason this login comes up is because of that simulation.
But why this log term and why not any other term?
Oh, so right now, okay, so right now the best thing that we know is the following. Uh, a universal, let us suppose that you have a Turing machine M, which runs
Yeah.
in time t, okay.
Hmm.
Then a universal Turing machine would require time order t log t. Right now, we don't
Hmm.
know anything better than this. So
Okay,
if
so
I think if you can prove something better, so suppose you could prove that there is a universal Turing machine that only requires t square root log t time. Okay, then I think
mhm,
you can improve this to square root log t.
okay.
Yeah. By the way, are you familiar with the non-deterministic time hierarchy theorem?
No, that I'm not aware
Yeah.
of.
So there
What is
is
that?
so basically you have over here you have d time on both sides, right?
Yes.
Over there is nd time,
Mm-hmm.
and over there fn and gn are like pretty close to each other. So over here the difference is log n, right?
Mm-hmm.
Over there the difference is like very small. You can almost think that fn and gn are very close to each other,
Mm-hmm.
and just gn is strictly greater than fn. That's it. No asymptotic relation. You can think of it like that. Okay.
Okay.
And the reason that you can do that is because I for non, if you allow your universal Turing machine to be non-deterministic, then you
Mm-hmm.
have a much more efficient Turing universal Turing machine.
So do we perceive UTM as deterministic always, or uh, I mean
Right. So okay. So
NTM also?
you can have your Turing machine to be deterministic or non-deterministic. What I'm
Yes.
saying is, so in the deterministic time hierarchy theorem, you would need a deterministic Turing machine, right?
Yes.
Right. So and the best thing we know for a deterministic Turing machine is a blow up of factor like log t.
Yes. Yes.
But
Yes.
for non-deterministic Turing machines, the blow up is much better. It's almost the same thing. It's like order t.
All right. All right.
Yeah. So I think yeah, the main factor is just this blow up that you get for a universal Turing machine. Yeah.
Okay. Yeah. Thank you.
Yeah.
Clear.
Okay. So let's move on. So after D space, you would have also seen the class N space, which is just a non-deterministic variant of D space. So N space Fn is a class of all languages decided by order Fn space non-deterministic Turing machines. And then you would have seen classes L and NL. So L is the class of all languages which can be decided by Turing machines running in order log n time. So L is D space log n, and NL is the non-deterministic variant of L. It is N space log n. Now it's easy to see that L is in NL, right? But proving whether this containment is strict or not, that's an open problem, just like P and NP. Okay. And you would have also seen the relationships between the classes d time, n time, d space, n space. And in fact, some of the problems that we would solve would involve dependencies between these classes. So the next thing that you would have seen would be log space reductions. So just as we have polytype reductions, we also have log space reductions. So a language A reduces to a language B in log space, denoted by A less than equals to LB. If there exists a log space deterministic Turing machine M, such that X is in A, if and only if M of X is in B. So over here we are using less than equals to L for log space, and for recall that for polytime reductions we were using this A less than equals to T P for polytime. Okay. Yeah. So then you would have also seen the notion of NL completeness. So just as we have NP completeness, we can also define NL completeness. And a language A in NL is said to be NL complete if for all languages B in NL, B reduces to A in log space. So this is analogous to the definition of NP completeness. It's just that this reduction changes. And you would have seen that the languages like path, A, acceptance by NFA, etc. are like NL complete. Then you would have also seen two theorems. The first one is Savage's theorem, which gives you the relationship between n space and d space. So it says that n space Fn is contained in d space Fn square. And then the second theorem you would have seen would be the Immermann-Celepseny theorem, which says that NL equals co-NL. Now these two theorems are sort of surprising because I don't know anything like this. So I don't do anything like this n time so we don't know whether this is true or not, and in fact it is believed that this is not true, because if this were true then this would imply P equals to NP. So even though whether P is equal to NP or not is an open problem, the analogous version for space complexity is not an open problem, it's well known. Okay, and similarly over here the analogous time complexity version is whether or not NP is equal to co-NP, but this is an open problem. Okay, so yeah, there is some sort of difference between space complexity and time complexity. They are not completely analogous to each other.
I have a query here.
Yeah.
Can we say anything about the cardinal? Can we compare the cardinalities of the sets NP and NL? Even though both are infinite sets, but still.
Right. Okay, so I think the best you can say is both are countable sets.
Okay, nothing more than that. I mean, can we say something like that the set NL has a less number of the problems in comparison to the NP set?
Oh, so that again, okay, so that's an open problem, right? So proving whether L is equal to P or not these two are open problems, right? So
Okay.
if this were the case, then what you were saying is true, right? So if someone is able to resolve this open problem in this direction, then what you said would be true.
Okay.
Right.
So what is our current understanding in relation to these different classes, that P is there inside NP and P and NP both are there inside D space, and D space is more or less same as NP space.
Right.
And so where are L and NL
Okay,
in this
so
entire
right now
hierarchy?
our understanding is this. L is
Mm-hmm.
obviously contained in NL. Now NL is equal to co-NL.
Mm-hmm.
NL is also contained in P.
Can you draw a diagram kind of a thing through circles so that it becomes easier to
Okay, yeah,
understand?
first let me finish this and then do it.
Okay, all right,
Because
all right.
yeah,
No
in case
issues.
like I mess, like there are too many circles, so in case I mess that up, at least we would have this.
Okay, all right. No
Yeah,
issues. Yeah,
and
please.
this
Please
is
continue.
in P space,
Mm-hmm.
and the reason we haven't defined an analogous NP space is because these two are the same. Okay,
Mm-hmm.
yeah, now let me erase this and try see if I can do circles. Yeah, let me also erase this. Okay, so this is L, this is NL, and this is also co-NL. Outside that we have P, outside we have NP, and outside we have P space. However, okay, so the way I've drawn these circles is that the circle for L is smaller than the circle for NL is smaller than the circle for P, smaller than the circle for NP and P space, right? But right now we don't know if there is anything in these. Oh, yeah, this color is not visible. Yeah, let me pick another color. Yeah. So right now we don't know if these spaces are, like, if any language exists in let's say we are not sure if any language exists over here or not, or that any language exists over here or not, or over here or over here.
Yes.
However, what we do know is the following: L
Right.
is strictly contained in P space. Okay, which means that at least one of these has to be a strict containment, right? Because all of these, if all of these were equality, then this won't be true. But we know that this is true. Yeah. So this is our current understanding.
All right.
Yeah. Okay. So in that case, let's move on to some problems. So the first problem is the following. So I think first 4 or 5 problems are theoretical. They just test your understanding of all the theorems that you would have seen in this week. So for example, a relationship between various PS classes and time classes and so on. So the first problem is, consider the following two statements. Statement P is n space n to the 4 is contained in d space n to the 8, and statement Q is n space n is contained in d space n cube. And select the correct option. So the options are: only the statement P is correct, only the statement Q is correct, both P and Q are correct, and neither of the statements are correct. So does anyone of you know the answer, or would you like to guess?
Is it C? Both are correct.
Right. And why is that?
Because of the Savage theorem, that whatever we
Right.
can do with the NTM in n raised to the power 4 space
Right.
can obviously be done with determining DTM in the space of the order of n raised to the power 8. And in the second scenario, we are giving more space than required,
Right.
so obviously that can be done.
Yeah. So as I said, this is Savage's theorem, right? And clearly n to the 8 is like n to the 4 square, and n cube is greater than n square. So yeah, there is enough space in both of these cases. So both statements are correct. Then the next question is, consider the following two statements: NL equals co-NL and NP equals co-NP. Which is definitely known to be true? Only statement P, only statement Q, both P and Q, and neither. So what's the answer to this question?
I think it's D, that we do not know. Wait. No.
Right.
We know that the statement number P is true for sure because of the Immerman thing,
Right.
and but we do not know for sure about the statement Q. So as per the current understanding, A is correct. Only statement P is
Right.
correct.
So because of the Immerman-Schlepp-Selepseny theorem, we know that NL equals co-NL. So P is correct, but whether or not NP equals to co-NP, that's an open problem. So this may be true, may not be true. We don't know. So the next question is, consider the following two statements. Statement P: d time n is strictly contained in d time n to the square root log n, and statement Q is d time n square is strictly contained in d time n square times log square n. So this is just log n to the power 2. And select the correct option: only statement P is known to be correct, only statement Q is known to be correct, both statements P and Q are known to be correct, and neither of the statements is known to be correct. So what's the answer to this question?
I think it's B, that we only know the truthfulness of the statement Q, and P is not correct because of that login factor,
Right.
Yeah.
Yeah, so what we have is this, right? D time Fn is strictly contained in D time Gn if Fn log Fn is equal to small o of Gn, right? Now over here the extra factor is just square root log n, which as far as we know right now may or may not be sufficient. So we don't know whether P is true, we don't know whether it's false. So we can't say anything about P. But over here the factor is log square n, which is definitely like n square log n square is in fact 2n square log n, which is definitely like smaller than n square log square n. So over here there is enough sort of blow up, but over here there is not enough blow up, at least according to our current understanding. So the only thing that we can say is that statement Q is correct. Yeah, so the next problem is, consider the following two statements. If A reduces to B in log space, then A also reduces to B in poly time. And statement Q is, if A reduces to B in poly time, then A reduces to B in log space. Select the correct option. Only P is correct, only Q is correct, both P and Q are correct, and neither is correct. So what's the answer to this one?
I think that in this case B is correct, that only statement Q is correct because of that hierarchy which you showed us in the beginning of this session.
Okay.
Since L is there inside P, so probably for P we require more time. So yeah, L and then NL and then P. Yes. So I think that only Q is correct. Only Q is correct. Yeah.
Okay. No. So the answer to this is only P is correct.
Uh, okay, and why
Yeah.
so
So
surprising?
yeah. So the reason is this. Okay. So okay. What does it mean to say? Yeah. So what does it mean to say that A reduces to B in log space? It means that there is a log space deterministic Turing machine such that yeah, so that there is a log space deterministic Turing machine such that X is in A if and only if M of X is in B, right? And over here B is a deterministic log space Turing machine. Okay. But we know that every deterministic log space Turing machine is also deterministic polytime Turing machine, right?
Uh, yes, yes,
Right.
yes. And
So
its converse is not true.
right. So over here M is also a deterministic polytime Turing machine. So you also have a deterministic polytime Turing machine that gives you this relation. So you can also say that A reduces to B in polytime, right?
Yes, so this answer is correct actually. Probably I misinterpreted the question because
Okay.
whatever we can do in the log space can
Right.
obviously be done in the polynomial time.
Yes. So
But
I think
whatever
you
we
were
can do in
saying
the
that, but
polynomial
you
time
drew the
is
wrong
not necessary.
conclusion, right? That is what you were saying, but from there you drew the wrong conclusion,
Yeah.
right? Yeah. So is this clear? Is this okay with everyone? Okay. Yeah. Okay. By the way, yeah. So if you notice over here, the statements, the options are not only P is known to be correct, only Q is known to be correct, and so on, right?
Yes, yes,
Yeah.
yes.
Because yeah. Okay. Yeah. Let's move on to the next one then. And okay. So yeah. So I think this is the last theory question. Yeah. So consider the following two statements. Statement P, d time n to the 4 is contained in d space n to the 4, and statement Q, d space n to the 4 is contained in d time n to the 4. select the correct option or options. Only P is correct. Only P is known to be correct. Only Q is known to be correct. Both P and Q are known to be correct, and neither of the statements is known to be correct. So, can anyone tell me which of these is correct?
I think that the option A is correct, because whatever we can do in the time of the order of n raised to the power 4 can obviously be done in this amount of the space, because space can always be reused.
Right. And yeah, so the answer is statement P is known to be correct. We don't know whether Q is correct or not, but suppose I wanted to make Q correct, so what should I write over here according to the current understanding? So if I wanted to make Q correct, I should remove this and write what?
Okay, so if we can write here, say D space, N space, we can write N
No, no,
space.
no, I want to write D
uh,
time over here.
okay, you want to write D time here.
Hmm.
So then 2 raised to the power n raised to the power 4.
Yeah, order n to the power 4, because over here there is an hidden order, right?
Yes.
Yeah. So this is our best understanding, right? So our understanding is this: D space
Yes.
of f of n is contained in D time of 2 to the order fn. Yeah. Yeah, so I think those were all the theory questions. Now there are some problems. Yeah.
Sir, what is the meaning of having 2 to the power order, right?
Oh, okay. So 2 to the power order n to the 4 looks like this: 2 to the c to the n to the 4. So over here c can be, suppose c were 2, okay, then this would be 4 to the n to the 4. Is this what you were asking?
No, no. Actually, what is this? I mean, this whole is in order of. What is this notation used for?
Like this notation, 2 to the order n to the 4?
Basically, this whole thing is the dating or what?
Okay, so I don't understand your question. Is it, oh, like, what is it that you are asking?
I'll ask in the last.
Okay. Yeah. So the sixth problem is the following. Suppose that L is equal to P. So like right now we don't know whether this is true or not, but for this question we have been asked to assume that L equals P. Okay. Then which of the following statements can be inferred from this? And we are supposed to select all the correct answers. So the options are P equals to NP, L equals to NL, NP equals to sigma 2, and coNL equals to P. So does anyone of you know which of these are correct? Multiple can be correct. Or would you like to
B
guess?
and B.
Huh?
B and D.
B and D.
Yeah.
Yeah, that's true. Like, can you tell me why?
Because as of now we know L is contained in NL and NL is
Right.
contained in P.
Yes.
Yeah, so like if we don't know that L is equal to P, then in the fourth problem also, like uh, can you please go to the fourth problem? Like
Right.
yeah, this statement. So here also it should be something like only statement P is known to be correct, only statement Q is known to be correct, right?
Oh no, so this is a reduction, right? So what you can do is the following. So A reduces to B in polytime, right?
Yeah.
So I can start off with like a, so okay, so when you do reduction, you are
Hmm.
supposed the okay, so you are supposed to write the output, right?
Mm,
Okay, and okay, so what would happen is this, right? There is a Turing machine M which writes down mx on its output tape, right?
right. Okay.
But if I want to do this and I
Hmm.
want to simulate M,
Hmm.
then this can't be its output tape, right? Because what this thing can do is this thing can go back and forth on its tape, right? Okay, so M is a
Yeah, I think
polytime
you
Turing
lost me.
machine, right? So it can go back and
I,
forth on its output tape, but
yeah,
that is not allowed for a log space Turing machine, right?
because in log space we are assuming it is only write-only tape.
Right.
For
So you can cook up something completely ridiculous, a completely ridiculous reduction where you keep on going back and forth and do basically nothing, and that won't be log space, right?
Mm, okay, but isn't that what actually we did in like to prove that if B were in L, then A must also be in L, right?
Oh no no! Over there you were like doing so. Over there, what was happening is like you were whenever you needed something, you took it, right?
Yes, exactly. But we were able to take it whenever we needed. We computed it again.
Right.
Okay.
So over, I
Okay,
think over
fine.
there, here there also like something similar turned up, right? Yeah. Okay, so we are here. Yeah. Oh, right. So yeah, you were saying that okay, L is in NL and NL is in P, right?
Yeah.
So if these two are equal, then these two also have to be equal, right? So that gives us B. What about D?
D is NL is equal to co-NL.
Right. Yeah. So that's essentially the solution. So basically, all of this was to show that NL is like L is in P, and then yeah, NL is in P, so NL is equal to L, and co and LN are the same. Okay. So over here, this option was fine, right? But over here, we are using the Immerman-Zalapseny theorem, right?
Yes, yes.
Yeah. And it is a very involved and complicated proof, okay? But what I'll show now is that if you assume that L equals to P, so if L is indeed P, then that's a very simple proof of the fact that NL and co-NL are the same, okay? So what I'm going to show now is not strictly needed for this problem. You can solve it using, as we did, using Immerman-Zalapseny theorem, but this is an alternative way of doing it without using that, okay? Just for option D, okay? Yeah. So the claim is the following: if A is in L, then A complement is also in L, and the proof is fairly straightforward. If A is in L, then exists a deterministic log space Turing machine M such that X is in A if and only if M of X is in B, right? So now what we'll do is, using M, construct another Turing machine which recognizes A complement but is a deterministic log space machine. So let N be a Turing machine that sort of flips the output of M. That is, for all x in 0, 1 star, nx is equal to 1 minus mx. So if mx is 0, this is 1. If mx is 1, this is 0. Okay. Now clearly n is also a deterministic log space Turing machine. Is this claim okay?
So I have a query here, that
Yeah.
is this always possible to flip the outputs, flip the outcomes? Because
Right.
quite possible that if we take the complement of the problem, the very nature of the problem may get completely changed, and the Turing machine may enter into something like, say, may take lots of time, may enter into a loop kind of a thing. So, is it necessary that if a problem is decidable in the log space,
Hmm.
its complement will remain decidable?
Okay. Right. So okay. So when do you okay? So when is the language decidable? If there exists a Turing machine satisfying this, right?
A language is decidable when we have the answer of both yes and no.
Right. So
So
that is
whenever the string,
exactly this statement, right?
yes,
Right.
here the answer of no is not given. Like, say, if a is decidable, then whenever x is the element of a, then we get 1 as the outcome, and whenever x is not the element of a, then
Right.
we should get the 0 as the outcome.
Yeah. So this statement means this. This double implication means this, right?
Yes, yes. Now it's correct.
Yeah. Which is just this. So because we're implicitly assuming, yeah, that the output is either 0 or 1.
Yes.
Yeah. So basically, M itself tells you that A complement is also decidable.
How is that necessary? That like say let us I mean can we take any an example of a problem which is decidable in L? Say path problem,
Right.
right? Even though the path problem is seems to be so well researched and well understood problem, can we take any other problem which is there in L except this path problem?
I think 2 sat is also in L.
Two set again is such a trivial problem. It is even there in P. I
Right. Okay. So
mean,
anything, if anything is in L, it
anything
has to
in
be in
yeah,
P, right?
true. So I mean, it seems that as if all those problems which are there in L are very trivial or very simple problems. Then probably there is a very limiting sense of the immerments proof that L is that NL is equal to co-NL probably.
Okay. So I think that actually that proof can be boosted to give you this. No, no, not this. Hence, yeah, is equal to co and C, where C is like any space class.
Mm-hmm.
So basically, it's not restricted to NL equals co NL. You can
Mm-hmm.
also using it. You can also, for example, show something like n space
Mm-hmm.
is equal to co n space. This actually is trivial, but something like this.
Great. So is this
Actually, this
applicable
is very
for
trivial because n space is p space, and everything that is poly n space is p space, right?
yes?
And co p spaces would be trivially p space.
Perfect.
Yeah,
So
but
is this a established fact that NC is equal to co-NC wherein C is any space complexity?
it has to be. So there are some technical constraints on what C has to be. For example, uh, I think it has to be space constructible.
Okay,
Yeah,
okay, all right,
you
all right.
can't do this for any. I think okay. A general rule of thumb would be it has to be greater than log n.
Great.
Yeah,
So this is totally a new fact. Thank you for
right.
this.
So basically, the
And
exact
now,
same proof works.
okay. So now if we consider two set problem, so if we take the complement of the two sets, so the problem formulation would be that it is not satisfiable. So if something is satisfiable and if I take its complement, will it become so can we flip the outcome in the case of the two set problem?
It depends. So if you are using a deterministic Turing machine, you can do it,
Hmm.
but you can't. So it's not the problem that matters; it's the machine that you use that matters.
Hmm.
So you can't flip the output of a non-deterministic Turing machine, but you can do that with a deterministic Turing machine. Because in a
Yes,
deterministic Turing machine, for any string, there are only two possibilities, right? Either there exists a path to the accept state, or there exists a path to a reject state, right?
correct.
So if there does not exist a path to the accept state, it
Hmm.
must mean that there exists a path to the reject state, right?
Correct.
But yeah, in the case of non-deterministic Turing machine, suppose there exists a path to the reject state, right?
Hmm.
Can you be sure that there is no other path to the accept state? No, right?
Not sure.
That's why you can't flip it. Because let's say you take a non-deterministic Turing machine n, it outputs 0, you make it 1, okay?
Hmm.
But you just saw one path of its execution, right? That
Hmm.
led you to reject. So basically, what I'm saying is this. If m were non-deterministic Turing machine and mx is equal to 0, then what this means is that there exists a path to the reject state, right?
Hmm. Correct.
But that does not mean that x is not in A, because there can exist another path to the accept state, right? So basically, what you are doing is you are just when you are flipping it, you are just looking at one execution and outputting, right? You're not looking at the entire graph.
Yes, but then that is what the meaning of the non-determinism is, that someone doing it for us and
Right,
correctly
exactly.
making a prediction for us.
Right, but when you are executing it,
Yeah.
you would have to verify that it. So if you want to use it inside an algorithm, you would have to
Hmm.
verify that it gave you the correct answer, right?
Yes.
Which the only way that we know of right now to do that is to basically execute everything. Like, look at the entire computation graph, right?
Yes, yes,
So that's
yes.
why right now we can't flip it. I mean, there might be a way to flip it, but we don't know how to do it
Correct.
efficiently. Efficiently, we
Yes,
can always do
yes,
it in exponential time. Yeah,
yes. So this
yeah,
is acceptable that if
right,
it is the case of the deterministic Tn, then yes, its complement would also be
right.
in L.
Yeah.
Correct.
So then M is also a deterministic log space TM because we are just executing M once, flipping it. That's it. Okay. So now X is in A complement if and only if X is not in A, which means because of this that mx is equal to 0, which means nx equals to 1, right? So what we have shown is that x is in A complement, if and only if nx is 1, which means n decides A complement, and so A complement is in L because n is a deterministic log space Tm, right? So is this fine?
Yes.
Right. So we wanted to show that co-NL equals to NL. So far we have shown that if a language is in L, its complement is also in L. Now we'll use this to show that NL equals co-NL. Okay. So what we'll do is we'll fix a language B in co-NL. Then by the definition of co-NL, B complement has to be in NL. And we are assuming that NL equals L. Right. So
Yes.
from the claim that we just proved, the complement of B complement, which is just B, is in L, which is NL. So B complement is in NL. So B complement's complement. So B complement's complement is just B, right? That is in L from the claim that we just proved, right?
Yes.
Right. And so that what does this mean? Any language in co-NL is also in NL. So co-NL is contained in NL. This is one direction, right?
Yes.
Now for the other direction, fix any B in NL. Then B complement is in co-NL by the definition of co-NL, right?
Yes.
But over here we saw that co-NL is in NL. So B complement is in NL.
Mhm.
Hence, B is in co-NL,
Yes.
right? Thus, co-NL is contained in. Oh
NL is
yeah,
contained in
this
NL
is
is
a typo.
contained.
Hence, NL is contained in co-NL. So
Yes.
here we have co-NL is contained in NL. Then over here we have NL is contained in co-NL, and so both are the same. Yeah.
Yes. Yes.
So if L is equal to P, then there is a very simple proof of this fact. You don't have to do the entire Immerman-Selefseni thing. Yeah.
Yes.
Yeah, but you don't
This
need.
proof,
Yeah.
this proof is almost similar. I mean, this is basically the proof that we use to say that P is equal to NP, then co-NP is equal to NP.
Right. Yeah. So basically, if you look at it, that's a very good point. But if you look at it, the heart of like both of the proofs is a claim like this, right? That if A is in L, A complement is also in L, and if A is in P, A complement is also in P, right?
Yes.
And I think actually that is true for almost any deterministic complexity class because of this flipping thing that you can do. Because
Okay.
the only
Yes.
thing we are using over here is a flip, is that you can flip it, right?
Exactly. Yes.
Yeah.
Yes.
Yeah. So if there are no questions, we can no other questions, we can move to the next problem. Okay. So the problem is Alice recently learned about the complexity classes NL and co-NL. She also learned that 2SAT and ANFA, that is the set of all languages that are accepted by non-deterministic finite automatons, are NL complete. However, she doesn't know of the Immerman-Schlesinger-Selepseny theorem yet. So she doesn't know that NL equals to co-NL, okay. However, if she wants to show that NL equals to co-NL, proving which of the following statements would suffice. Select all the correct answers. So the options are 2SAT is in co-NL, 2SAT is in NL, the complement of A NFA is in NL, and the complement of A NFA is in co-NL. So which of the following are correct? Multiple can be correct. So would anyone of you like to venture a guess?
Yes, so I think that option C is correct. That if the
Okay.
complement of NFA is there in NL, and since all the problems which are there in NL can be reduced into ANFA, and now one of the, I mean, its complement is NL, so therefore ANFA is also there in co-NL. So C is correct, and then based on this line, probably A would also be correct. So A and C are my, I mean, best choices, I think.
Okay. Yeah. So so those are the answers. The reason is basically what he was saying. So we know that 2 sat is NL complete, right? So if 2 sat is in co-NL, as every language in NL reduces to 2 sat in log space, A is all every language in NL is also in co-NL. This might have been covered in class, but even if it's not, it's the proof of this is exactly similar to the proof of the following, that if A reduces to B and B is in L, then A is also in N. So if this hasn't been covered in class, it's very simple. You can try it on your own, right?
It was covered in the
Okay,
class. It was.
okay, yeah,
And but I have a query here that is this
right.
true only for L and not for any other known complexity common complexity classes like say for NP or for
Right,
some other
yes.
class?
Yeah. So this is only known for like complexity classes of the form N, C, and co-N. C, where C is some space complexity class, reasonable space complexity class. Right.
Can you repeat this? I could not hear you
Yeah. So
properly.
the thing that we discussed before. So this is known for the classes of the form NC and co-NC.
Yes, okay. Now I
Right.
understood.
We have in C
Yes.
is some reasonable space complexity class.
Yes.
Yeah.
Okay. Which is space constructible.
Right. Yes. Yeah. So this proves that NL is in co-NL. Now I think in the last problem we showed that if co-NL is in NL, then NL equals co-NL. Here we'll do the exact same thing but in the opposite direction. So here we'll show that if NL is contained in co-NL, then again co-NL is contained in NL. The proof is exactly the same. Pick any B in co-NL and its complement has to be in NL, which is in co-NL, right? So if B is in co-NL, this implies that B complement is also in co-NL. Therefore, B is in NL and so co-NL is contained in NL. So both are the same. I mean, you could have as well done this uh, using like the Immermann-Zelepseny theorem, but the point over here is that Alice does not know this theorem. So we are supposed to prove everything without using that theorem. Okay. So is this fine? Yeah.
Clear. Yeah.
Yeah. And we can do the same thing with the other thing, right? So the other language of was ANFA is NL complete, right? So what we'll prove is the following. If ANFA is NL complete, then its complement has to be co-NL complete. And then using the exact same argument as the one over here, we can argue that that would mean that NL equals co-NL, right? Is that fine or should I repeat it?
Yes. It's
Yeah.
clear.
Okay. So all we want to prove is that ANF is NL complete, right? Sorry, this complement is co-NL complete. Yeah. So okay, what does this mean? This means that for every language in NL, there exists a deterministic log space Turing machine M such that X is in A if and only if M of X is in ANFA, right? But
Yes.
this implies that X is in A complement if and only if M of X is in A NFA complement, just the contrapositive of this, right?
Yes.
Hence, A complement is log space reducible to ANFA complement. Again, reduction is again just M, right? Thus, A complement NFA is co-NL complete, which is what we wanted to prove, right?
Yes.
Yeah,
So we were not supposed to prove co-NL completeness. We were supposed to only show that without using that Immerman result,
right,
how can we show that NL is equal to
right.
co-NL?
Yeah, so the reason we proved that this is co-NL complete is the following. If this is co-NL complete, and we
Mhm.
show that this is in NL, then using the
Mhm.
exact same argument as before, we would get co-NL equals is in NL, and then NL equals co-NL, right?
Yes, yes, correct.
Yeah, so the reason we did this was because, so the first thing that we did in this slide was to show that this option is correct, right?
Yes,
Yeah, then the thing that we did in the next two slides was to show that this option is correct, also correct, right?
yes,
Yeah,
yes.
yeah. So if there are no questions, then we can go to the next problem. Okay, yeah. So the problem is the following. Suppose we have a graph on n vertices and we need to run a loop that iterates over all the vertices, okay? Then what should be the space requirement of the counter in terms of number of bits that is used to keep track of this loop?
So is this option B the order of log of n?
Yeah. And why is that?
Because to store a number n, you require log n number of the bits.
Yes, right. Ceiling log n, but yes. So basically what we want is we want to count n vertices. So we want a counter that goes from 1 to n. Or alternatively, since we are computer scientists, a counter that goes from 0 to n minus 1 will also work, right? Now,
Yes.
to store any number less than n, we need ceiling log n number of bits, right? But ceiling log n is less than or equal to 2 log n. So to store the number 0 to n minus 1, we just need at most 2 log n bits, which is just order log n, right? So we can use a counter, we can have a counter that just uses order log n bits.
Yes.
Yeah. So the next problem is, consider the problem of adding two given n-bit binary numbers a and b. Okay. Given as a simple string in the format an minus 1 up to a1, bn minus 1 up to b1. We need to output the sum a plus b in the binary form. Okay. And what is the space requirement of the most space optimal algorithm to execute this using a deterministic Turing machine? The options are O1, O log n, O log square n, O square root log n, and On. So which is the, like, which of these is the correct answer?
I think it is again the option B only. We require log n amount of the space because space can be reused. Once I add an and bn, I just need to keep the track of the value n and then I can reuse the same space. So probably I would be requiring the space of the order of log n only again. In this case also.
Right. So even though the number of bits is n, you are saying we just need order log n bits, right?
Yes.
Okay. Yeah, yeah, that's the answer, and that's because. So what we'll do is we'll perform addition bitwise,
Yes.
and so now, okay. Now suppose I give you A and B on two different tapes. Okay. So here is the tape for A, and here is a tape for B. Suppose this were your input model. Okay. Then how many bit? Then what would be that space complexity?
Uh, can you please repeat
Okay.
your
Yeah.
your
So the
query?
input model is this.
Okay, so now the inputs have been given on two different
Right.
tapes. Okay, and fine. So then, if they are on the different tapes, then how does it matter to me? Then also I would be requiring log n amount of the space only. Uh,
No, in that case, you can do order one, right? Because you have two tapes, you have two read-write heads, right? Two independent read-write heads. So what you
okay.
can do is you can start with initially both heads would be over here. All you would do is
Yes.
the following: you would store some carry bit, which you can do
Yes.
just using just one bit.
Mhm.
So you look at the the carry bit, the bits where your
Mhm.
head are, add the three up,
Mhm.
write down the answer of the output tape,
Mhm.
and then move your head one space to the left.
Yes. So
You're only
then it
using the
can be done.
carry bit, right?
Yes.
So that's what the second statement says. we need at most constantly many bits to store the intermediate sum and carry bits. Okay. However, because we are given input on a single tape, we have only one read write head, right? So this is what our tape looks like. Yeah, so this is what our tape looks like. an minus 1, a1. Then there is this hash that separates the two. bn minus 1, b1. Okay. Now, my claim is, if this is the situation, you need to store n, or rather you need to store I, the index of the bits that you have processed. Okay. So is this clear why? The claim is, however, we need a counter that counts till n to keep the track of the number of bits of a and b that we have added so far. Is it clear why we need this counter?
Yes, because we would be adding an to bn and an minus 1 to bn minus 1. So therefore, we need a counter which varies from 0 to, 1 to n.
Okay, no. But over here we are also doing the same thing, right? We were adding an to bn, an minus 1 to bn minus 1, a1 to b1. We still didn't need a counter over here.
Yes, we were doing counter, but then here we are using an additional output tape and
No, over here we are also using an output tape.
yes. So
the only difference between these two things is that over here you had two input tapes, one containing A, another containing B.
but then
Over
in
here
this
you have
case
just one tape.
we are having two different processing elements also in this case.
Right. So over
Whereas
here
in
we
this
have
case,
two different heads, right? And the way we
yes,
were keeping track of which indices we have processed is by moving these heads, right?
yes,
However, over here we have just one head, right?
yes,
So
yes,
if I want to add A1, what I would have to do is move my head to A1, write down A1 on my work tape, move my head to B1, write down B1 on my work tape, add the two, write down A1 plus B1 on my output tape, write down the carry bit on my work tape, then go to A2, go to B2 and repeat this process, right?
yes,
So after I've completed this first step, I need to know that now I am supposed to go to 2, right?
yes,
And that is what exactly what this counter tells us, right? Which bit which are supposed to access now, which over
yes.
here was told to us by the read write heads.
Hmm.
Yeah, so is this clear?
Yes,
Yeah, so the counter again, counter counts up to n. You can make it count from 0 to n minus 1, anything. So you need order log n bits. Okay, is this fine?
yes, and I asked this question in one of the previous problem session also, that it also depends on that how do we describe the problem size, because whenever we find that this log stuff is important, so we start considering the space occupied by, or we start talking about the counter kind of the thing. Otherwise, in the normal algorithms, we used to mention that the problem size is equal to n, the number of the elements in the list. There we do not take the help of this counter. We take the help of the concept of counter kind of the thing, wherein only log n amount of space is required to store something, while determining the complexity and
Oh, no. So
determining the
even
size
over
of the.
here, we would, so even suppose you had an algorithm that runs in order n time, okay, that would still be your polytime algorithm.
Uh,
So even over here we are defining the complexity in terms of functions of n only, right?
yes,
That is exactly what we are doing over there, right? We are defining the complexity in terms of the input size. Over here we are also doing the same thing, right? Because the input size is 2n, 2n plus 1,
yes. Input size is 2n plus 1,
right?
correct?
And log n is just a function of 2n plus 1, right? I mean, I could have written, so I have written log n, but I could have written this in terms of log of 2n minus something and something like that, right?
Yes,
Yeah,
yes. But that is nothing. In fact, that can
right.
safely be ignored.
Yes, exactly. Because of this order. So even over
Yeah.
here,
So
we are So basically always, unless otherwise mentioned, the complexity would be measured in terms of the input size. Okay.
Mhm.
Yeah. Yeah.
Clear.
So for the last question, so consider the statement coNL is contained in D space log to the kn. Okay. What is the smallest integer value of k for which this statement is true? So what's the answer to this one?
So, what is the smallest value of k for which
This is known to be true.
this is known to be true? Uh, so space and
Okay, suppose instead of NL, co-NL you had NL, then what would be true?
so if it is NL, then because it is deterministic, so for deterministic, I require the square amount of the time. So I would have said that k is equal to 2 because in case of because NL is equal to co-NL and NL
Right.
is contained there in the n space of log of n,
Uh,
right? But then what is the relation between n space of log of n and then the d space of log kn? So
in fact,
if we
these two
take
are
the help
equal,
of the
right?
Savage theorem, then
Right.
probably the value of k would be equals to 2, I think.
Right. So we are basically using Savage's theorem over here and Immerman-Zelepseny theorem both, right?
Yes,
The second one for this and the Savage's theorem for this, right?
yes.
Yeah. So the answer
This
is two,
value of k is equal to 2,
right?
correct? Okay,
Yeah.
yeah.
Okay. So over here in the first step we used uh, Immerman-Zelepseny theorem, right? But you can actually do this without a theorem as well.
Okay, how?
Yeah. Okay. So this is just from Savage's theorem. NL is this is Savage's theorem, and the second step was Immerman-Zelepseny theorem, right? What we want to do is we want to remove this now. Okay. And I think the proof of this would be similar to some of the proofs that we have seen before.
Yes,
Yeah.
yes.
So what
In the
we
case of the deterministic TM, this is true.
right. So yeah, as we discussed before, right? This claim is true for deterministic Turing machines because you can flip things around, right?
Yes.
So yeah, in that case, let me skip this proof. Where does this proof end? Yeah. Uh, yeah. Okay, right. Yeah. So what this tells us is that if A is in D space log square n, then A complement is also in D square log space n, right?
Yes.
So what we can do is pick any language. Let me do it. Yeah. Pick any language A in this should be co-NL, right? Then A complement is in NL, which implies A is in D space log square n. Is this fine? Sorry, A complement is in D square log space n. Is this fine?
Uh, this is fine.
Right. Now from this claim, A is in D space log square n. A complement is in D space log square n. Right. So
Yes.
now A complement is in D space log square n. This implies A is in D space log square n from this claim, right?
Mhm.
So over here we replaced A by A complement and A complement by A. So we started off with an arbitrary language in co-NL and
Mhm.
proved that it is in D space log square n without
Mhm.
using Immerman-Zelepseny theorem, right? Just Savage's theorem.
Yes.
Yeah. Yeah. So that's it for that's all the problems for today. So if you have some questions, you can ask here. Otherwise, we can end.
So, is there a simple proof of the Immerman's theorems? Because this proof was covered in two lectures, and
Right.
really it is difficult to understand. I mean, can you suggest us some animation through which, or some other resource through which this can be understood well? Even though sir explained it quite well, but still it is too long that it is difficult to follow.
Yeah, I don't know of any simpler proof.
Okay,
Yeah.
okay, okay.
Yeah, but I think he would have also covered like a way to break down the process of creating a certificate into the process of creating smaller certificates, right?
Yes, but the proof itself is actually difficult. Like say the Cook-Levin theorem, so there are
Right.
few animations kind of, I mean, stuff is
Okay.
available,
Yeah.
which helps to understand actually. And this Immerman proof is new to me.
Yeah. I don't know of any animations or something like that for this.
Okay,
Yeah.
okay. And what is so very special about this log stuff? Why do we pay special attention to L and NL and not to the other form of the other form of the functions,
Okay.
like
So
some other function, like say instead of log, some other function?
okay. So suppose okay. Okay. So first of all, the functions less than log are not very interesting because you can't even remember the head position of your the head position of the head of the input tape, right? If you don't have
Yes,
log in space,
yes, okay,
right?
yeah, true.
And for functions above log, like one natural function is this, right? Uh, order n. One natural function is
Hmm.
just linear, right?
Hmm.
But the problem of whether L, okay, so the problem of whether deterministic linear space is the same as non-deterministic linear space, that's an open problem. In fact, you would have seen this even in the TOC course. Does this
Yes.
remind you of something?
In case of the space log.
Deterministic linear space and non-deterministic linear space.
But then, in the case of the space, we have the Savage theorem, and then we do not differentiate in between the determinism and the non-determinism much.
Oh, can you see that again?
So, in case of the space, we do not differentiate much in between the non-determinism and the determinism.
Right. So that is obviously one reason why you don't like look at very. Let's say for example you don't have a class NP space, right? You just have P space.
Yes.
But what I'm asking is the following: let A be the class of all languages, which are
Uh-huh.
decided by deterministic linear time Turing machines, and B be the class of languages decided by non-deterministic linear time Turing machines.
Okay, time
No, no,
wise.
no. Sorry, space.
Okay.
Okay, yeah. So A is the set of all languages
Mm-hmm.
decided by deterministic linear space Turing machines,
Mm-hmm.
and B be the class of languages decided by non-deterministic uh, linear space Turing machines. Okay.
Yes.
First of
So
all,
again, both are
does
both are
Savage?
equivalent.
No,
Both
no,
are
no.
equivalent.
They both are the both functions are n, right? So I'm talking about d space n and n space n, right? Savage's
Yes.
theorem only tells you that d space n is contained. Sorry, n space n is contained in d space n square, right?
Yes.
It doesn't tell you anything about d space n and n space n, right?
Yes. True.
Right.
I understood. Yeah.
Yeah. So uh, what I'm saying is this is an open problem, and you would have also seen this open problem in the TOC course. Can you recall this? I mean, it wasn't mentioned in this form; it was mentioned in some other form.
So probably you are asking for a problem which is decidable by a non-deterministic Turing machine in the linear space,
Right.
and which is not decidable by a deterministic Turing machine
Need
in
not be
the,
decidable. We don't know. It's an
yeah,
open
will
problem.
not be decidable in the same linear space. So uh,
Okay. What is a Turing machine? which can only use linear space called. It is a name,
Li-
right?
Linear space?
So what is a Turing machine which can only use linearly many tape cells called? It is a name.
Linearly
Linearly bounded automata, right?
LBA.
Right.
Yes.
And what is the language? What is the set of languages that are
Context
accepted?
sensitive, context
Right.
sensitive. Yeah.
So the open problem is whether CSLs, uh,
Uh,
so whether CSLs and like context sensitive languages decided by deterministic Turing machines and those by non-deterministic Turing machines are the same or not. So whether deterministic linear bounded automata and the non-deterministic linear bounded automata are same or not. That's the problem, right?
okay. So is this an open problem of for LBS?
Yeah, I think it's an open problem because at least 2 years back it was, and I haven't seen. I don't know if anyone has proved it, but I don't
Okay,
think
okay.
anyone has.
Okay, because
Yeah,
usually in the TOC course, LBAs are not being taught.
yeah,
So only finite automata and then PDAs and then state way. Syllabi moves to the Turing machine
right,
and doesn't cover the
yeah,
LBAs because they view LBA as a special type of the Turing machine only.
right.
So what is the formal definition of the LBA then? That
Turing
LBA is a
machine that can
Turing.
only use like linear space in the input. So basically, all the sort of D space and Turing machines.
Okay, okay, okay.
Yeah,
Thank you for this.
yeah. Okay, yeah. So if there are no other questions, we'll meet next Friday at the same time.
I
Yeah,
have.
yeah. Okay,
Okay, so that to keep our own problem,
yeah. Can you
if
speak a little
we write,
louder?
hello, now can
Yeah,
you hear me?
yeah.
Okay, so that to keep our ON problem,
Okay, right.
if we write n square, then we can define values 1, 4, 9, and etc.
Okay.
But if we define 2 keep our ON, what are the values we can define?
Okay. Okay. So that's your question, right? Okay. So n square is 1, 4, 9, and so on, right? And you are asking what is 2 to the power n to the 4. Okay. Okay. Now, okay. So first of all, you know that order of fn is not just one function, but it's a function class, right? Hello. I couldn't hear
Sir,
you.
yes, sir.
Yeah. So when you say that some function is 2 to the order n to the 4, you are actually saying this, right? Some function which belongs to this class, right?
Yes, sir.
Now, depending, okay, so hidden inside this order, there is a constant, right? So basically what I'm saying is f belongs to 2 to the order n to the 4 means that f is equal to 2 to the c to the n to the 4 for some constant c. Now as you change constant c, your function also changes, right? So for example, you can as well take c is equal to 2, in which case you would get 2 to the 2, 2 to the 2 times 4, 2 to the 5, which is 2 to the 32, and so on. So when we say that some function is 2 to the order n to the 4, we have some constant in mind which we are not specifying.
Okay, sir.
Yeah, and this need not be
That's
a constant. Like this can be, f can also look like this, right? 2 to the n to the 4 plus n cube plus n square and so on, right?
okay, sir.
Yeah, basically this entire thing is a function class, and we are hiding the exact function inside this class. Pick any function that from this class that would give you a specific f, and then you can start writing its values. So is this fine?
Okay, sir.
Yeah.
Uh, if we say that one theorem can solve a problem, what is the meaning of it?
A theorem can solve a problem. A
Uh,
Turing or a Turing machine.
Theorem or basically a algorithm.
Okay, so okay, so saying that an algorithm can solve a problem, the same as saying that a Turing machine can solve a problem, right? Because an algorithm and Turing machine are the same thing.
No, no. For example, there is a problem P versus NP.
Okay,
We ask what algorithms can resolve the problem P versus NP question.
okay, so one algorithm that can resolve. Okay, so basically there are two ways to resolve this question, right? So the question is this: whether P is equal to NP or not, right? There are two ways to resolve this: prove that P equals to NP, or prove that P not equals to NP, right?
Okay, sir.
Now, algorithms can help you with only this part. Why? Pick any problem which is NP complete and come up with a polynomial time algorithm for that problem. Okay, that would prove this.
Okay, sir. So, if there is a problem, for example, the CSAT algorithm,
Right.
so it is not a polynomial time solvable algorithm.
As of now, yes.
Okay,
Right.
so this can resolve the P versus NP question.
Right. So if you can come up with a polynomial time algorithm for 3 sat, then P would be equal to NP, right?
Okay,
Because 3 sat is
sir.
NP complete. So every language reduces to 3 sat. So if you can solve 3 sat in polynomial time, you can solve any language in NP is also in polynomial time, right? Reduce to 3 sat, solve 3 sat.
Actually, sir, there was a question which was the following choices will resolve the P versus NP question, and
So
this was a previous assignment which has been marked.
okay,
So,
so what was the exact question?
in which of the following choices will resolve the P versus NP question?
Okay, and what were the choices?
A polynomial time algorithm for three coloring,
Okay,
polynomial time algorithm for two coloring, a
okay,
proof showing that three set does not have a polynomial time algorithm,
okay.
and a proof showing that two set does not have a polynomial algorithm.
Oh, the answers would be A and C. A polynomial time algorithm for 3 coloring and a proof showing that 3 coloring or 3 sat is not in P.
Sir, why not B?
Oh, so 2 coloring not in a polynomial time algorithm for 2 coloring, right?
Okay.
Is that what you are
Okay.
asking?
Yes, sir. Yes. Sir.
Okay, so the thing is 2 coloring is not NP complete, right? In fact, 2 coloring is itself in P.
Okay. Sir.
So if you come up with a even if you have you have a algorithm for 2 coloring, but that does not allow you to solve some problems in NP, right?
Okay, sir.
Yeah, but if you had something for 3 coloring, and since 3 coloring is NP complete, you pick any language L in NP. First, reduce that language to 3 coloring in polynomial time, and then solve 3 coloring in polynomial time, right? So poly plus poly would still be poly, right?
Okay, sir.
Yeah.
Sir, I am getting a bit difficulty in identifying which is in P and which is in NP.
Okay,
So,
so
can I get a list or something of it?
I think even if you search, so I know that there is a list of all NP complete problems, like all well-known NP complete problems listed somewhere, but I don't remember the exact like place.
Okay, sir, can you tell this me next week?
Yeah, so I would have to look it up because I knew this like 2 or 3 years ago. I've forgotten what that uh, website was called. Yes, I can try looking it up.
Okay, sir.
Yeah.
So, there was another question. Sir, for two colorable algorithm,
Hmm.
what is the fastest time complexity or
Mm,
the time complexity of the fastest algorithm?
I don't know. Like I know it's polytime. I don't know the exact polynomial.
So, sir, how should we attempt questions coming in the exam?
Okay, so right. think the two coloring problem is not that difficult. Let me see, try to see.
Should I tell you the exact question?
Yeah, what was the question?
So the question is, suppose an undirected graph G is provided as an adjacency list.
Okay,
Suppose G has n vertices and m edges. Which of the following represents time complexity of the fastest algorithm to determine whether J is too colorable?
okay. So what are the options?
The options are ON,
Hmm.
ON plus M, ON log M, OM log N, ON square plus M square.
Okay, so I think for this you would have to come up with an algorithm.
Sir, actually, the
So
algorithm
will
I
it
came
be
up with,
will it be of the order of n dot m then? Because since that graph is stored as an adjacency list, so
Hmm.
for every vertex we have to refer to the attached adjacency list. So there are n vertices and then there are m something.
Hmm.
So whether two adjacency vertices are having same color or not. So for every vertex we have to search m times. And since there are n number of the vertices, so either it would be of the order of n dot m or order of n plus m probably. Yes, BFS, right. Yes, so yes,
Right. Oh
yeah.
yeah.
So and BFS runs in the time of the order of v plus e.
Right. So
So
m plus
therefore,
n.
yeah. So therefore, it would the answer would be probably of the order of n plus m. I'm not sure.
Oh wait, but BFS. Okay, yeah, BFS order m plus n when the input is adjacency list, right?
basically, I was told that BFS was solved in B square plus N time, E time.
Okay. No, but so what's the best complexity for BFS? I think it's yeah, it's
Yes,
size of v plus size of e, right?
yes,
Yeah, so I think yeah, you can always solve B space in like BFS in higher time, but yeah, the best known is this, right? So I think yeah,
So,
for this you would have to try to find an algorithm that's it.
okay, sir. Thank you, sir.
Yeah,
Sir, please do provide me the list in the
yeah,
next class.
yeah. Okay.
That's all, sir.
Ye- Yeah,
thank you
yeah.
very much for
Thank you.
today's session.
Yeah,
So I'm leaving now.
yeah,
Thank you very
yeah.
much.
Thank you. Bye.
Bye.